Thank you for that introduction, Martina, and thank you to the Program Committee of the International Astronautical Federation for giving me the opportunity and the privilege to address you all tonight. Okay, I'm going to talk about astronomy from the moon and the cornucopia of science that it could deliver, but also some of the challenges it faces in being able to continue that activity sustainably. So if you haven't heard of doing astronomy from the moon, that's not surprising, because even a few years ago, almost all astronomers, including me, thought this was a silly idea that had no value at all. Not all, but there were a small clique who persisted in pointing out the usefulness. But as plans for a human base near the South Pole have emerged and become more imminent, astronomers started to realize that if you have astronauts and you have tons of equipment being landed on the moon, all within a decade, that becomes an interesting parameter space to start thinking about, can we put some telescopes on the moon? And it becomes a real opportunity. So around the end of the pandemic in early 2023, I helped convene a meeting at the Royal Society on astronomy from the moon, and we gathered about 50 astronomers from in London from all over the world for 2 days of talks about these new concepts. And they brought up ones I certainly had never heard of, spanning most of the electromagnetic spectrum, from the ultraviolet to the radio, the very low frequency radio, and even in gravitational waves. And this meeting seems to have generated some momentum and led to several professional meetings afterwards, and we're on a roll. I hope you'll see why. So why the excitement? Because this science that we can do spans an enormous range, from the dark ages of the universe, before there were any stars or galaxies, right up to finding nearby alien civilizations, should they exist, or at least life on other exo-Earths. So I'm going to limit myself to 5 examples, and I'm nobly and restrainingly not going to tell you about the Elvis-Karovska method of measuring the metric of the universe. You can ask me about that later. But as I wrote the talk, I realized there was a theme here, and that is that our computer simulations have become so good that they look so convincing in the videos that the people produce from them, that we feel convinced that they must be right. But in fact, in many cases, we have no data to test those models. And astronomy from the moon may enable some of those tests to take place. So here's the first example out of 5. It's a plot of the first billion years of the history of the universe. That's until the universe was 10%, a bit less than that, of its present age. So it's the early baby pictures almost of the universe, stemming from the Big Bang on the left to the first formation of stars on the right. And the first stars seem to have formed around redshift 10, 12, maybe a little higher, after a few hundred million years of the universe becoming in existence. And that era is being wonderfully observed and opened up to the investigation by the James Webb Space Telescope. And we needed the James Webb Space Telescope because this is all happening at a redshift of 10, which means the universe was 10 times smaller then and has since expanded by that factor. And that stretches out the light from the normal optical ultraviolet bands where we study stars locally into the infrared. And that's what James Webb was designed to do, and does it beautifully. But you'll see that there's this gap called the Dark Ages, when there were no stars, and that seems like maybe there was a quite boring era, but in fact, no. In that era, we went from parts per million of fluctuations in density over the whole universe to places where the density becomes so high and the temperature becomes so high that hydrogen burns and fuses into helium. In other words, the middle and insides of a star. How does that enormous range of density and temperature come into existence? We have simulations of what must be happening. They look convincing, but are they right? We don't have any data from the Dark Ages to test that. There is just one possibility. There's the one thing there was a lot of in the early universe is hydrogen, and hydrogen has one line, one emission line, one transition in its atom which can absorb or emit at a wavelength of 21 centimeters or 1.4 gigahertz in frequency space. And that is a tool we use locally in the universe, very much so, to map out the structure of the Milky Way or to see streamers of hydrogen gas pouring from one galaxy to another. But that's great locally at 21 centimeters, 1.4 gigahertz, but unfortunately, we're now talking redshifts of nearly 100, and so that radiation emitted at that 1.4 gigahertz has been stretched out to be 100 times longer wavelengths, and that is a problem for detecting it. What about life? And example 2, what about life and detecting aliens? Well, we are protected by the Earth's magnetic field from the radiation in space, from the solar wind and so on. So if we could work out which exo-Earths, meaning terrestrial-sized planets in the habitable zone where water can be liquid, which if we also we're able to filter on those which have magnetic fields, that would focus our attention onto more promising Earth-like planets. So what we could do with the low-frequency radio emission is measure their aurorae, like the aurora australis here, and that would tell us that there was a magnetic field protecting the surface of that planet. If we want to be more dramatic, we could ask if any exo-Earths have technosignatures. Are they emitting radio waves as we have been for about a century now? And can we set limits on how much they do that, even if we don't detect them? Or maybe we would detect one. Apparently, this can be done out to perhaps 100 light years from here if you had the right telescope with the right sensitivity. But the problem is, and old people in the audience, senior people in the audience, will recognize this as a tuner for a radio. And I got it because it mentions the actual frequencies we're talking about. We're talking about tens of megahertz here, and that's a problem because that's where we are emitting lots of radio emission. So the noise on Earth is huge, not to mention the atmosphere is a problem. And that makes the Dark Ages and alien life undetectable from Earth. Third example is listening to the hearts of giant stars as they explode, supernovae. After 50 years of trying, computer modeling of supernova explosions failed to make them explode. They would be failed explosions. They would try to expand but collapse back. But we know that they do expand. This is a Chandra X-ray Observatory image of the Cassiopeia supernova remnant, and each one of those different colors is a different element that was created in the supernova explosion, being forced out into the interstellar medium, where eventually it becomes condensed into stars and planets and in fact, us. This is where the star stuff comes from. We are star stuff. Chandra has measured this Cassiopeia A supernova remnant over 20 years now, and it's been able to see that those little filaments have been expanding. And you can tell how fast the thing is expanding, and of course you can then extrapolate back, and it's about 300 years old. So now, most recently in the last couple of years, it's been thought that we've solved the problem of making supernova explode. And the key was in that the explosions are very much due to three-dimensional effects that only exist in 3 dimensions, so you have to have a very full-up 3-dimensional simulation. And they are very non-spherical. So here is a high-resolution image of this from the model. This is a full 500 milliseconds after the first explosion, and yet already you can see it's extremely non-spherical. And what you can't tell from this picture is that there are outflows, of course, from the explosion, but there are also very fast inflows, which keeps the energy density high and keeps the explosion happening. And so this is the claim that we now understand how supernovae explode, or so we think, but this is just theory. There was no test of this model, because how do we test what happens in the first half second of an explosion inside a star where we can't see what's going on? And they're very complex models, so could some of the nuclear physics be wrong? Could some of the neutrino physics be wrong? There's a lot of possibilities for making errors in these things. We need to test them. So how do we test them? One answer is to use this asymmetry, because when you have large masses moving very fast in a very non-spherical way, that's exactly the conditions you need to generate gravitational waves. And so that's going to be an interest, and that has a signature which some calculations say comes at a particular frequency that can only be detected, guess where, from the moon. If we look at the stars, they look like twinkling points of light, and we tend not to think of them as real objects in their own right. And even if we did, you might think, well, we don't really need to image the stars because they're kind of boring. This is a picture of the sun, and there's not a lot of information in that picture. Why should we go to a lot of trouble to image stars if that's what they look like? The answer is that's not really what all stars look like. If we can make hundreds times sharper images than Hubble or Webb, but only for the brightest stars, with using an interferometer. There are two in existence. One is on Mount Wilson in California, and it made these images of stars showing lots of very strong star spots, that not everything is spherical, but squeezed. In fact, they can be quite irregular in shape. The problem is, why don't we just keep using this? Well, the problem is the atmosphere wobbles so much that the integration time you can have, the exposure time, is just a millisecond, after which the turbulence in the atmosphere changes the phases of the photon wavefront coming in and makes it impossible to see fringes, which is how interferometers work. So, and if we could get better signal to noise and cover all the scales available, then Betelgeuse is predicted in a complex computer simulation to look something like this. It's a three-dimensional boiling pot of convecting water, well, of course, it's plasma in this case. And it would be a movie, because this stuff is moving quite fast, and we could watch how that turbulence happens. If you can image stars, can you actually image exoplanets, exo-Earths in particular? When I say image, I mean not just detect a point of light next to a host star, but actually make an image that can do enough to see whether you can see oceans, continents, a mixture of those, cloud cover, and just possibly vegetation. That would be a wonderful thing to be able to do, but of course this is visionary. It's beyond what we can do at the moment, and would be, even on the moon, would be a distant prospect. But I'll show you what might happen. So I hope you find those 5 examples reasonably compelling to say, we wish we could do that science, how are we going to do it? And so obviously I'm going to tell you that we use the moon to do that, and I'll show you how that would be done for each case. So for the low-frequency radio that we would like to use to measure the dark ages and look for life elsewhere, the answer is to move your telescope to the far side of the moon. That's actually the Parkes radio telescope in Australia, and I don't mean to be stealing it from you, so excuse me. What's great about the far side of the moon is that it's extremely radio quiet. Here's a data analysis challenge for you. This is data at various radio frequencies as a time series as this satellite RAE2 orbited the moon. And the trick is, can you tell when it goes into the far side? Okay, hint, this is the near side. Yes, the signals completely disappear to the sensitivity of this experiment anyway, when you go on the far side. The actual degree by which the background noise from the Earth is cut down, 2,000 kilometers of rock, that's pretty useful. The actual factor by which it's reduced is predicted to be absurdly low. Here's a image, a calculation of how much the gain is. Anything red or darker is at least 80 dB down. That's 100 million times fainter than the front side. I don't think there's any other case in astronomy where you can look for a factor of 10 to the 8 improvement in your background or any other criterion you choose. So this is pretty darned remarkable. Is it true? Well, we can only tell if we go there and check. So already as a result of this, and before our meeting in London, this was a active field. Several people had ideas of how you might do this. Here's half a dozen of them, starting with a clever Chinese proposal to have a chain of satellites in orbit around the moon, separated by probably 100 kilometers altogether. And when they go around the far side, the far side, they would be able to start imaging the background and see if they can find this signal from the dark ages. And then there are various possibilities on the ground on the far side, and I can show you there's a European one, two NASA ones, another Chinese proposal, and the ultimate telescope for this purpose would need to be 200 kilometers in diameter. It's just an array of dipoles, but it's still big. And at that point, you resolve all of the 1 million gas clouds that eventually combine to form a single galaxy. And this overcomes some of the problems with using galaxies to determine the structure of the universe, because the universe just doesn't have enough galaxies. So the good news is there's going to be, even next year, there will be at least one first measurement, so long as the landing goes well, but it's Firefly, so it should do, on the far side, to actually check out whether the noise level is that much lower than we thought, than as predicted. Excuse me. The gravitational waves are an interesting case. Woo! It requires the prediction by some calculations is that the characteristic signal of supernovae exploding will take place in a region of parameter space of frequency of gravitational waves that we have not yet probed. In a few years, the LISA mission from ESA will probe very long wavelengths and be able to see black holes merging in distant galaxies. Already we have LIGO, Virgo, and CAGRA taking measurements on the ground. They work at higher frequencies and a much shorter wavelength, much shorter measurement arms. But that leaves a gap which is about 2 decks wide, a factor of 100 wide. And guess what? That's exactly where some calculations say the characteristic signal of supernovae lies. But you can't do that, you can't examine that frequency range on Earth because of noise, both seismic activity and human activity, trucks driving by, basically. And of course, the moon is far quieter in seismic activity and has no, currently, human activity. So that's very promising. So how are you going to do it anyway? There's 2 approaches. The first one is to put a kind of super LIGO on the moon, this time in a triangle and 40-kilometer sides instead of 4. That's a problem because you can't put it anywhere on the moon because the horizon is just a few kilometers away. So the trick is to put it on the edge of a crater, which of that size, so you can have a clean line of sight across. You'd really like to have a cold, cryogenic environment because the mirrors that are hanging there and reflecting the laser beams have thermal noise in them, and if you can reduce that, you can increase the sensitivity of your detector, and you can do that by not going down a little bit into the permanently shadowed regions of your chosen crater. The alternative is to measure the distortion of the whole moon using seismometers. The moon gets squished and pushed by the gravitational wave, the quadrupole nature of the gravitational wave. Please note, this is wildly exaggerated. Not just wildly, it's absurdly exaggerated. The true motion is a small fraction of the width of a proton. And yet this is apparently, and I'm no expert, apparently detectable. So this is a proposal for a lunar gravitational wave antenna led by Jan Harms of Gran Sasso. And you can see here in the design that they were clearly channeling R2-D2, but nevertheless it seems to be a good design. It's again cryogenic, and the idea is to have an array of these around as much of the moon as you can cover in order to triangulate the position from which the gravitational waves has arrived, because that will allow you to look in other wavelengths for electromagnetic counterparts, whatever wavelength. Again, permanently shadowed regions are favored because we like it to be cold, and a lot of the power goes in cooling the first part of the cooling cycle. It's down to like 50 Kelvin. And one of these would be great for studying the inner structure of the moon. So maybe we can join forces with the lunar scientists, and this is far more sophisticated seismometer than they are currently planning to put on the moon. It would be good to land just one of these, not the whole array, just to see that what the seismic background truly is at the levels of interest. If we want to image the stars like Betelgeuse, then you have to have a telescope that's 100 times the diameter of Hubble or Webb. And that means you're moving up to kilometer scales. And certainly you can't have a single reflecting mirror there. You have to use an interferometer. So here is one example of how that might work. You put telescopes out on the lunar surface. Here's for scale, JWST, and you can see how big it is. Each of the telescopes sends its light to a beam combiner, which measures fringes between each pair of mirrors, of telescopes. This particular one is taken from the Artemis-enabled stellar imager study, led out of Goddard Space Flight Center, which seems it's quite ambitious. They want at about 30 1-meter class telescopes. You need a lot to cover a lot of different baselines to get fill in the image properly. The key thing is, compared with doing this on Earth, where you have 1 millisecond, you can easily observe for 1,000 seconds, so 1,000,000 times longer, and that will give you at least 1,000 times better signal to noise. So it's really quite a dramatic breakthrough. You can also look at far fainter objects, stars that are much fainter than we can do on Earth. But why put it on the moon and not in orbit? Well, they studied that. You need precision flying, formation flying of 30 different spacecraft separated by tens or hundreds of meters, and to a tolerance, a fraction of a wavelength, which means at the longest 0.1 microns. If you can get into the ultraviolet, it means 0.01 microns, and that's extremely challenging. Instead, when you put these telescopes on the surface of the moon, they just stay put, and it simplifies the technology greatly, so long, of course, as you have that human base to be able to deploy these. And lastly, how would we build a big enough telescope to make an image of an exo-Earth? This is a slide, a publicity slide from the European Southern Observatory. Their current big telescope is the Very Large Telescope, which you can see sort of just at the bottom of the central pyramid there. They're building, after the Very Large Telescope, they're building the Extremely Large Telescope, which is they have on the left there, 39-meter diameter primary mirror. And getting up to proper pyramid scale. But that's actually a step down from what they first looked at building, which was an overwhelmingly large telescope with a 100-meter mirror. And just for those of you not used to measuring in units of pyramids, here's a football pitch instead. It's about that size, which is a pretty awesome thought. So they decided that although they'd love to build that on a big mountain site out in Chile, it could not be done because of wind shake, because of gravity sag, and because you're still trying to be diffraction limited at 10 times the diameter of James Webb Space Telescope, and that's a real problem when you're underneath an atmosphere, wobbling atmosphere. You have to make corrections with clever, fast-moving optics called adaptive optics, and the complexity of those is said to scale at least to the cube of the diameter of the mirror. So it all gets it rapidly runs away as a problem, a technical problem. But of course, as you all know, none of these are going to be problems in space because there's no wobbling atmosphere, there's no or reduced gravity, and there's no wind. So what you ask, why not put this telescope in a JWST-like Sun-Earth L2 orbit? My mistake, I got carried away and obsessed with the moon here. Don't believe what I've written. Why not? Well, giant telescopes take a lot of construction, and you can't do a folding spacecraft, a folding mirror, the way JWST did, scaled up to fit a starship. That's still much too small. So you've got bound to do complex assembly with many single-point failure modes out at L2, and that's very challenging. It's very complex. You can't use people to help you out there because the radiation is deadly. So it must be assembled by robots or tele-operated from the ground or from orbit. But that's got an annoying multi-second delay because it's 1 million kilometers away. So basically you've got a real problem. And once you get it built, you've got to point this telescope at different exo-Earths or other targets. And that means giant reaction wheels, because this has to end up being a massive device. And your accuracy to which you point and keep steady the pointing direction has to be 10 times better than James Webb Space Telescope. Extremely demanding. So surely expensive, and really that's quite discouraging. But at our London meeting in 2023, Jean-Pierre Maillard suggested a whole set of reasons why the lunar surface just might be the better place to do this. There was no sunshade needed because you use a permanently shadowed region. So slewing is easier, deployment is easier. There's no need to have onboard solar panels. In fact, if you're in a permanently shadowed region, that would be stupid. But you can put an array of solar panels on a nearby sunny ridge, which so means you can have much more power than you are otherwise limited to if you tie it to the spacecraft. So you're decoupling the systems. You can also eliminate a number of systems. There's no need to maintain the orbit with propellant, and because the moon is going to stay in its orbit regardless. And so the lifetime is not limited by that. It might be limited by other things, but there's no inherent limit because of that. You don't need reaction wheels because you're pushing against the surface of the moon, which is fine. So slewing is much easier. And you're on the moon's surface, which is a very stable platform, so it's reducing the problem of jitter, but not eliminating. I'm sure there will be mechanical problems, but issues, but certainly making it a lot easier. And servicing, which is bound to be needed and has been demonstrated to be a very powerful effect with the Hubble Space Telescope, you can't do that very easily at L2. It has to be all robotic and pre-thought out. If you have humans, astronauts at your lunar base with supplies coming in by the ton, then it's going to be much easier to service and repair than at L2. Altogether, Jean-Pierre suggests that these together might mean that we can do a cheaper mission and perhaps may even make the whole mission feasible. Not by any chance immediately. This is clearly a distant prospect even now, even with bases on the moon, but it certainly shows great promise. So what are the sustainability challenges I mentioned in my title? There are several. I should have said challenges instead of threats. It sounds a bit too aggressive. For the low-frequency radio, it's unintended electromagnetic radiation, which comes not from the direct communication channels which happen at gigahertz frequencies, but from stray noise from the electronics, the electrical systems like power supplies and motors, winding harnesses, wiring harnesses. And that happens in the megahertz range, which is just where we want to observe the dark ages signal. So that's a problem. On the moon, any kind of gravitational wave, it depends deeply on having low seismic activity, and human activity could contribute to noise, so you want to make sure that your gravitational wave detector is a good distance from your base, where the landings and takeoffs and mining equipment might be operating. So we don't know yet how far away that ought to be. That has to be studied, but it's clearly a concern. And for the optical, infrared, and ultraviolet interferometry, dust is the real problem. And dust can be kicked. If you're in a permanently shadowed region, you don't get the lofting by the UV radiation that causes dust to rise up about 1 meter, but instead you do have the possibility of launches and landings creating enormous amounts of regolith and sent off in all directions at a low angle, and that could cover, if that coats your mirrors, you're in real trouble. And mining is a more ongoing possibility than landings and launches, which you could just shut down for and cover up the mirror. But if there's mining going on, like water mining in a permanently shadowed region, then that could be a continuous source of dust that you have to worry about. And, well, none of those possibilities are regulated whatsoever at the moment. The types of the threat you're looking at can be global or can be local. And the global one we know about is the timing PNT constellations around the moon, which are being planned. The ESA Moonlight one, I believe, is the most advanced. There's the Lockheed Martin Parsec system, but I heard at this meeting that maybe that has been mothballed. There is a Chinese system being planned, and I'm embarrassed to say I couldn't find the name of it while I was looking. And again, just at this meeting, I discovered there's a Japanese system being built. So there could be 4 systems going to be in orbit around the moon and producing that electronics noise that we call UEMR. The problem is that each satellite system has to have 4 satellites overhead at any one time to get to all the information about your position and time. So with 4 systems, that would mean 16 satellites overhead. So each individual satellite has to be cut its noise, not by an amount that individually can get you below the threshold that would be a problem for radio astronomy, but 12 or 16 times lower than that. It's the aggregate that matters. The fix is probably pretty simple. We're talking about multi-meter wavelengths for the radio emission from these electronics. And so a chicken wire, centimeter scale mesh would prevent most of that radiation getting out. A simple Faraday cage, Faraday screen. But of course, the engineers who are building these systems have never heard from the astronomers because we've only just woken up to this problem, and we need to be able to communicate with those people. So if any of you are involved and know people who are doing that, I would love to hear from you. If you look locally, it's surprising how rapidly the options for where to put a telescope shrink down once you put in different criteria. So for instance, we wanted a permanently shadowed region for a 40-kilometer on a side triangular gravitational wave detector. Well, there's only 3 craters at the South Pole which are permanently shadowed and 40 kilometers or so in diameter, and they are Shoemaker, Hayworth, and Faustini. But 2 of them are rich in water, from what we can tell, and so we want to avoid those because they're likely to be good mining targets, being very close to the South Pole, and we want to avoid all the vibration and dust from them. So it could be that there's actually just this one crater, Faustini crater, where we can put this telescope. It's a first analysis, we may find more, but it shows that they're rare. Previously, a pretty unknown feature on the lunar surface, and yet it could be key to making these measurements. So the general lesson we found as we look at different cases is that these lunar sites of special scientific interest, SSSIs, we got to learn to say that easily, are typically rare and typically quite small. And that means we need to think about how we can protect them for use for astronomy to preserve our science options, even if building this gravitational wave detector is decades away. How can we now ensure that there is a place to put it that is pristine and properly useful? On the other hand, the good news is they're typically rare and small, which means we're not asking to put half the moon or some huge area off limits to commercial or exploration activities. We're just asking for a few small spots on the moon. Now, rare, valuable real estate is known to be a great cause of disputes and conflicts, and the question of how we go about protecting these SSSIs is an urgent one. And in particular, who will adjudicate any dispute? How will we settle a dispute? That's a big unanswered question. What we're doing about it is working under the auspices of the International Astronomical Union. They were very quick to have found a working group on astronomy from the moon just a few months after our meeting in London. And I have been made a co-chair of that, along with Chris Johnson of Secure World Foundation. I don't know if he's here. And Richard Green of University of Arizona, who's the chair of this and spends a lot of time in Vienna as a result nowadays, which is where UN COPUOS meets, the Committee on the Peaceful Uses of Outer Space. The goal is simple, and that's protecting these SSSIs. But to do that, we have 4 priorities. We've got to identify and justify the choice of these SSSIs. We've got to help develop reasonable policy or legal frameworks for designating them. And we need to work with all the different bodies involved, particularly with the COPUOS. The ATLAC Action Team for Lunar Activities Consultation was also rather quickly put together. I may have missed the backstory here, but it seemed like we said, oh, we need something, and it sort of happened very quickly. So maybe UN COPUOS does not deserve the reputation for slowness that it has often been said to have. And then we're working with other regulatory groups, and we'd love to work also with other international organizations that want to protect other sites on the moon, such as the Apollo landing sites, which need protection, clearly, or other lunar science sites, where perhaps the coldest of the cold traps in the permanently shadowed regions have the best record of solar system history in volatiles that would otherwise be evaporated, or if mined out, if you go water mining there. That would be a shame if all of those disappeared. So what I've been working on is identifying and prioritizing these SSSIs. We're working with the PI teams, and the point is to develop a quantitative chain of reasoning that goes from the most general statement, like we want to measure these dark ages of the universe, using a science traceability matrix approach, where we drill down in each of the criteria, through the instrumentation, through the background, and therefore through the sites, and end up with figures of merit for each one of these sites, which allow us to rank them in order of importance. At the same time, we've been involved in several actions, and I'd like to highlight the very recent, last May, I believe, formation of a United Nations Friends of Lunar Sites of Special Scientific Interest. Several delegations have signed on, so it's very promising. And we also we're working with the Lunar Policy Platform and with COSPAR to work on a guide to lunar science and ethics, helping to put together the way in which you would designate these sites. So that's all very detailed. Let's not, however, step back and remember the vision, which for me is that we will want to understand our universe from our nearest neighbor world, and at the same time avoid repeating the mistakes we've made in low Earth orbit and on the ground. And what we do matters, because we are the first generation setting up this system. And as Wilbur Zielinski said, even a few score initial colonizers, he was thinking of the 13 original colonies of what became the United States, can mean much more for the cultural geography of a place than the contributions of tens of thousands of immigrants a few generations later. So the cultural geography of the moon is something we will be setting in this generation. And let us hope that we set a good example that will persist for a century to come or more. Because if we get it right, we will understand the universe and our place within it, and we'll be the better for it. Thank you. This says, anonymous. Some astronomers worry that lunar telescopes could weaken the public's connection to astronomy, since Earth-based observatories inspire future scientists by welcoming in-person public visits. How might moon telescopes continue to inspire? Well, the public, that's great. The public can't see the great telescopes that NASA puts into orbit, and yet is still impressed by the results from them, and they often, results from James Webb Space Telescope often appear on the front pages of major newspapers. I would think that's the path forward. There will still be observatories on the ground, I'm sure. They can do things that could not be done easily from space or not cost effectively. So there will still be great observatories to go visit. Let's see, what else do we have? How do I anticipate space objects that have the potential to hit the moon, considering the moon has no atmosphere? Yes, they do. There have been collisions with the moon. You see occasional flashes from small meteorites. What is the name of that asteroid that was going to hit the Earth? No, then it wasn't, but it still has a 4% chance of hitting the moon or something like about that. Yeah, that would be a problem. It could ruin your seismometer if it gets too much of a kick, I imagine, but they'll probably have a guard against that. Finding them, well, the question is, how big would they have to be a real problem? And NASA is funding the Near-Earth Object Surveyor, which I think will be launched in 27, maybe 28, which will be very good at finding near-Earth asteroids that might hit the Earth down to some size limit. There's always a limit. I think it's of order 50 meters diameter, so something 20 meters across would escape detection. Also, of course, we have coming online very soon is the Vera Rubin telescope, which is conducting a survey of the whole sky, and is very good. If you saw their press release image, it's amazing what you can do in detecting asteroids. They had dozens of them zooming across the picture. It was very impressive. So between them, you'll find most of the bigger asteroids, meaning down to about 50, 100 meters. So that can be, big ones can be ruled out, small ones we have to accommodate. Oh gosh, there's a lot of questions now. Any budget estimations for such a project? No. I think the bigger ones are all currently beyond the pace, our ability to make a good estimate, because we don't know the properties of the human bases on the moon and whether the rate at which they can get equipment landed and the cost of landing that equipment. So we're far away from that. But the early Pathfinder ones, like Lucy Knight, or a single seismometer, or a simplified version of the interferometer with maybe 2 or 3 mirrors, those are costable, I would think, at the moment. And of course, Lucy Knight is actually flying, so it must be quite cheap. I don't know the number. What role can rovers play to support these missions? They can, if you saw, many of them have multiple components to them, like the gravitational wave detector. You have to have 3 of them, and you'd land them all in one place and have a rover with astronauts go around the crater rim and in place them. And the same with the interferometer and the optical. You'd have astronauts deliver the 1-meter telescopes and put them in the right places and put the beam combiner in the middle. And that's probably a necessary step rather than having them land. You could, of course, have individual landers go in the right and hope that they can land very precisely. But landing next to a delicate telescope is a dangerous thing to do because you kick up the regolith. You probably need rovers with astronauts. If all of the lunar satellite constellations proceed, will useful radio astronomy still be possible? Well, it will if we can persuade the owners of these and developers of these constellations to put a Faraday cage around the electronics. I think that would pretty much solve the problem. You need an in-depth analysis to see just will it be enough. But the intuition is that it should be enough. We'll see. And so if that's the case, no problem. If it's not the case, we probably are in trouble. Yes. In a future likely push for commercialization of the moon, how could we ensure that astronomy remains prioritized, or at least not completely sidelined, in future lunar development? Yeah, it's a problem getting a seat at the table, considering science to be an equal partner with commercial and exploration activities, I think is something we should be trying to do, and we are trying to do. The Artemis Accords only mention science once. I think it's in Article 11, Paragraph 11. But you could build on that single mention to bring a scientific voice to the table. We'll see if that succeeds. I read somewhere that some of the moon crater sides are crumbling. Does this affect any of your favorite SSSIs? Maybe, and I have been looking for papers that describe how well we know how crumbly the rims are. They are, of course, made of rubble, because that's how the crater formed. Is that rubble consolidated enough over the course of the last billion years or so to make it safe to put a telescope on the edge, a gravitational wave detector, or in the case of a radio telescope that's made out of a dish made out of a crater and pegged at the rim on several places, is it going to last, or are those pylons at the edges just going to collapse in? I don't think we know the answer, but I haven't got a definitive reading on that. If anyone knows, I'd like to hear about it. Who do I think should lead telescope development on the dark side of the moon, such as NASA, ESA, private industry, or international consortium? I don't know. It depends who has the will to make it happen. At the moment, the United States doesn't seem likely to go to a huge installation on the far side, but we are making steps to test the environment. That I don't think we can predict. Usually these things end up as collaborations. They may or may not. I think this means, okay. Could existing or near future lunar missions really realistically transport and assemble the infrastructure needed for a functional observatory? Possibly. We don't know, and the more we input, the more we think about it, the better the inputs we can give to the designers of the landers, of the astronaut EVAs, and of the rovers, and maybe we can help adapt those systems to be useful for astronomy. Why are there no active volcanoes or liquid water on the moon today? Because it's cold. The whole of the moon is cold all the way through. Gosh, what do you see as the most difficult technology / top 3 to develop this telescope? It also says brilliant talk, but I wouldn't brag. Oh, it disappeared. Oh, here we go. Oh, the most difficult technology. Well, they're all difficult. We don't do easy things, otherwise they'd have been done already, and that would be pointless. No, I think I need to be more of an expert on the technical details of each one of these, and I rather fear that nobody is an expert on all 5 of them. So that's a bit of a cop-out. I'm sorry. Perhaps perhaps we should stop soon. I don't know. Yes. How about this is a big one. What do you think about moon colonization and exploration? Interesting. I did put some numbers in about if you put a city on the moon, how long would the water last, right? And if you use water for propulsion, as hydrogen and liquid oxygen, then as you burn it, it's gone, right? Because it's distributed all over the cislunar space. So that's a one-time use. But even if you recycle water as efficiently as the International Space Station, which is like 98% per cycle, then the water is gone. Then half the water is gone after 50 cycles. Now, the total amount of water on the moon could be as much as 1 billion tons. That's a 1 kilometer cube. It would fill, if you poured it into a container, a sort of aquarium that included all of Central Park in Manhattan, it would fill up to the height of the tallest skyscraper that there is there on the sun. So that's sort of, it's a lot from one perspective. It's if you had 1,000 people on the moon, living on the moon, that would last for a few thousand years. But if you had a town like 100,000 people, and so more of a true colony, not that we like that word, it's true settlement, that would be gone in about a century. And it's not retrievable. So we have to. So I think there's a big physical problem in going from scientific bases, even quite large ones, to an actual functioning town or city. So I think that's a kind of problem that really is going to take a lot of thought to see if there's any way around that limit. And maybe I should stop. I don't know if. No, my introducer has disappeared. So there are more, but I don't want to bore everybody. Yes? 5 minutes. Oh, I've got 5 minutes. I'm reading incorrectly on the thing here. Going back to the topic of crumbly rims, given the role of an atmosphere in developing structural integrity of rocks, is it less likely we may find suitable rims on the moon? That's geology. I'm sorry, I really don't do that. I'm a poor old astronomer who doesn't understand geology. I'm not going to answer that. How does the current budgeting status and government feeling towards science as a whole in the US affect my personal outlook for the realization of these observatories in the future? No comment. You talked about the complexities of building an exceptionally large telescope at L2, but what about the complexities of building in a permanently shadowed region? Temperatures in the PSRs can be down to minus 250 Celsius. That's correct. And building something in a cryogenic situation maybe that is the biggest technical challenge. I hadn't thought of that. That will be really tricky. I assume you assemble a lot of stuff as modules before you take it down and hope you can clip them together once they're in place. Not all the temperatures in the permanently shadowed regions are that cold. That's like 25 Kelvin. And that is the coldest of the cold traps, of the permanently shadowed regions, which we've looked at for putting an far infrared telescope down there, because that would cut the high infrared background greatly. It was one of the ones I left out of the talk. But some of them are 100 degrees warmer, above 110 degrees, which is an interesting number where water starts to, if you get hotter than that, water sublimates in a vacuum, so that they will be anything warmer than that, even though it's permanently shadowed, will be dry. And they go up to, I think, about 150 Kelvin. I would have to look. So there are more moderate, still challenging, but more moderate places on the moon you could go. Would the extremely thin atmosphere of the moon be suitable for precise optical surfaces needed for EUV and X-ray optics? Yes, and Poshak Gandhi of Southampton has written a paper in our proceedings on that topic, and he suggests that there are cases which would be interesting. An X-ray interferometer would get micro-arc second resolution very quickly, because X-rays are very small, so you don't have to have a big diameter. And so those have not really been explored much. There's a professor in Amsterdam who's looking at X-ray interferometry, which could be a very interesting and exciting field. Oh, well, that's nice. Somebody else is being nice to me. I better not brag. Most applications presented require high sensitivity. Could I explain why tidal effects are not a problem? I don't think I see the problem, so maybe you can come up afterwards and we can talk about it. What time frame are we looking at before lunar telescopes become the new normal? Well, in 10 years, we'll have done the preliminary investigations, I suspect, of all these different possibilities, and we'll know which ones are easiest to go ahead with or even feasible at all. And then it will take, I don't know, 10 years back minimum to get a full-up version of one of these. So it's of order 20 to 30 years from now, we'll have these. And once they're there, they will exceed the capabilities of other telescopes by orders of magnitude. And so that will, in a sense, be the new frontier, the new normal. I hope. How long have we got? Another minute? Let's see if there's anything else here. If you did have a telescope on the far side of the moon today, what's the first thing you'd look at? Which type of telescope? I like the Dark Ages. That's a really amazing concept. But perhaps if I had a giant telescope, I would like to image an exo-Earth. But that's, as I said, the most distant of the prospects, because you actually need an array of very large telescopes. So that's beyond what we can imagine doing for perhaps 50 years. But the point that I was making about the challenges is, even though it's something maybe 50 years away before we can do it, we still need to pin down the best locations where we'd like to put that, so that we can keep that location in pristine condition. And that's the big challenge now. More even than the technology is the legal and governance issues involved. So I think I can stop there. Okay, thank you very much.